Okay, so we defined how we can add vectors and how we can multiply a scalar and a vector. And we did this in a very arithmetic way. And I want to kind of motivate what these operations look like if we were to try and represent things geometrically. So we've seen pictures of vectors before. So if I have a vector, for example, in R2 that I'm denoting V, if it's in R2, it has two components we'll call V1 and V2. So these are both scalars. So we can represent this vector in R2 as a directed line segment. I'm going to start the line segment at the origin, and I'm going to end the line segment at a terminal point whose coordinates have x1 is equal to v1 and the second coordinate is equal to v2. So here is a little directed arrow corresponding to this vector, which is v1, v2. So recall when we added two vectors, we needed them to have the same dimension. So if I have two vectors u and v in R2, then we could compute the sum of these two vectors by adding up u1 and v1 and then u2 and v2. But let's see what that would look like in the plane. So I've got this vector v and I've got this vector u over here. So one way that I can think about adding to these two vectors would be, let me first travel along vector u. So I'm first going to go along this direction to take care of this. Then I'm going to go along direction v. So I'm going to start vector v where u just ended, and then I move along the direction v. So over here, I just drew this vector v. Rather than start it at the origin, I'm going to line up the tail of this vector at the tip of the previous vector. And now the sum of these two vectors is actually, I can think of as the diagonal of the parallelogram that's spanned by the vector u and the vector v. So this is what we call the parallelogram rule for addition. And that is if u and v are in R2, then their sum is going to be the diagonal of the parallelogram spanned by these two vectors. So this works if we're working in R2. If you're not all that familiar with working in higher dimensions, I'll just say that we have a similar interpretation in R3 as well. Next, I want to similarly reframe scalar products in this geometric way. So if I have a vector u and I'm multiplying it by some non-zero scalar c, then what this scalar is going to do is it's going to represent a scaling factor towards this vector. So for example, if I were to try and calculate what is 2u, well, we talked about how the arithmetic would work. We would just multiply every component of u by the scalar 2. And what that looks like in the plane in R2 would mean I go u and then I go u again. So now I have a vector which is parallel to the original u, but twice as long. If we were to multiply by a negative scalar, just keep in mind that in addition to changing the length of the vector, it's also going to flip the direction around. So for example, that vector over there is the vector minus u. So when we multiply by a scalar, a couple of things might happen. First of all, we're going to get a vector which is parallel to the original vector u. If the scalar is positive, then we're going to wind up with a vector that has the same direction. If the scalar is negative, then we're going to wind up with a vector that, although it's parallel, it's going to be pointing in the exact opposite direction. So that's what the sign tells us, whether we're flipping the direction or not. And then the magnitude of this scalar is going to tell us whether or not we're stretching this vector or whether we're compressing it. So if the absolute value of c is less than 1, then the vector u, when I multiply by this scalar, is going to get shorter in magnitude. So we're going to call that a compression. And if this scalar c happens to be larger than 1, then we're going to wind up with a vector whose magnitude is larger. So that's going to be a stretching of the vector u. So we can think of addition of two vectors in R2. We should be thinking about parallelograms and the diagonal of a parallelogram. And if you want to picture what does scalar multiplication do, what is the scalar product? Well, that's going to be a rescaling of the vector. And I want to summarize some really useful properties of vector arithmetic on this slide. But before I do so, there's one really special vector called the zero vector. So just like the number 0 is a really important number in our number system when we're working with vectors, this zero vector is going to also be a really important concept. So we can represent the zero vector as either a bold fonted 0 or with a 0 with an arrow above it. And here, again, we want to be really, really careful that we're making this distinction between the vector 0 and the number 0. And if you're writing things out, it's really hard to tell the difference between bold and regular font. So I would definitely encourage you, again, to use this arrow notation. So the 0 vector is the unique vector which has no magnitude. And so, in other words, equivalent way of saying that is that it is the vector that all of its components are 0. So it's just a vector of all 0. So we have different 0 vectors. We have a 0 vector in R2, which would just be 2 zeros. We have a 0 vector in R3, which would be 3 zeros, and so on. So depending on what dimension you're in, the 0 vector is actually going to be different, but whatever dimension you're in, it's going to consist of a column vector of n zeros. And so down below, I just summarized some of these important properties that the textbook lays out. So we're going to let bold-faced u, v, and w be vectors in arbitrary Rn space, so it doesn't matter how big what the dimension of these vectors are, but they all need to have the same dimensions. And we have two scalars that we don't put in bold, c and d. Then what we get are some pretty familiar looking results. So the order that we add vectors does not matter. This would be the commutative law. If I want to add 3 vectors together, it doesn't matter which 2 I add together first. So this would be like the associative law. When I take u and add the 0 vector to it, it doesn't change the vector u. I get back u. So that's kind of how the number 0 works as well. If I take a vector u and I add to it exactly the same vector in the exact opposite direction, this is basically saying we're going to move u and then we're going to move exactly in the opposite direction of u. So you wind up back where you started, which means you haven't gone anywhere. So we get the 0 vector out here, but this is not the number 0. This is the 0 vector. And for scalar multiplication, if I multiply a scalar times the sum of 2 vectors, it's the same as multiplying the scalar times u and the scalar times v, and then adding those 2 together. We have a similar distributive law if I'm multiplying the sum of 2 scalars times a vector. And we have a similar associative rule with scalar products. So if I take c times the vector du, it's the same thing as taking c times d and then multiplying by u. And so all of these properties are not too tricky to actually prove and verify that they work. So if you want to convince yourself of these properties, it's not a bad idea to try and prove that they work in the general sense.